Hello, everyone. My name is Eric Chan. I'm a PhD student at the University of California, Riverside, and I'll be presenting this brief announcement by Mohsen Lasani and I, titled Brokering with Hash Timelock Contracts is NP-hard. So HTLCs are a type of smart contract, and in 2018, Herlihy described a protocol that utilizes HTLCs to exchange assets between different blockchains in an atomic manner. So we'll be considering these things in the context of brokering. So brokering is allowing parties to leverage assets that they would gain during the transaction, whereas Herlihy's original protocol required that all parties own all of their assets at the beginning of the transaction. So here we don't consider a specific implementation of brokering, just brokering as a high-level action or abstraction that parties can partake in. So we're in this work, we're interested in a special transaction graph type called flower graphs. The name comes due to the topology of the graph. But flower graphs have exactly one broker, and all edges in the graph are incident to this broker. So meaning parties don't swap amongst themselves, and they only swap with the broker. Additionally, parties other than the broker all have their assets at the beginning of the transaction. So why these graphs are interesting is because they represent a market clearing service if they were to commit to the protocol themselves as a broker. So they'd have all parties swap to them instead of directly to one another. And in that case, perhaps the broker or the clearing service can obtain a commission for each of the swaps. So the problem we're interested in is the minimum leader set problem. So the minimum leader set problem is using Herlihy's protocol, find a set of leaders that eventually creates all of the contracts such that this set is minimum. And why this problem is important is because the global transaction fees of the protocol scale directly with the leader set size. So if we minimize the number of leaders, then we minimize the total gas costs of executing the transaction. In Herlihy's work, though, he also notes that any leader set is necessarily a feedback vertex set. So if we want to find a minimum leader set, we need to find a minimum feedback vertex set. However, we know that problem already to be NP hard. So in this work, what we actually first do is we increase the difficulty of the problem by introducing the brokering capability. So this directly implies that brokering on transaction graphs is already NPR generally. But what we're more interested in doing is decreasing the difficulty by restricting the graph type to the flower graphs we previously described. So overall, the question becomes, is finding a minimum leader set on flower graphs NP hard? And by the title of the talk and by the paper, the answer is yes. It remains to be NP hard, and we'll show that by a reduction from the famous knapsack problem. So as we all know, a knapsack instance K is defined by a triple XVW, where X is some set of items, where each item is defined by a pair V, which is a value, and W, which is a weight. And the goal is to find a subset of items R such that the sum value of R is at least V without exceeding the weight capacity W. So here we'll just provide an intuitive step through of building the reduction rather than a rigorous analysis of our construction of the reduction. But overall, the idea is that we're going to construct the flower graph F that essentially forces the broker to solve the knapsack problem. And how we can do that is first we'll create a node that we call the supplier. We'll call that node S, and then our single broker B. So S will give B W Bitcoin, where W is the weight capacity described in the original knapsack instance. Then for every item in the knapsack problem, we'll create a corresponding item node that receives W in Bitcoin, or WI in Bitcoin, where WI is the weight of that item, in return for VI ethers, where VI is the value of that item. So in the figure in the bottom left, we can see that essentially S is supplying the broker with W Bitcoin, and the broker needs to use those W Bitcoin to exchange with each item node to eventually retrieve V ethers. And then in that case, what we can do is if we're given this decision procedure, DMLS, which stands for decision minimum leader set with parameters G, which is a transaction graph, and an integer K, let this be a routine that decides whether there exists a leader set of size K for the graph G. Then we can just run DMLS on our flower graph F and 2 to decide whether the knapsack problem is satisfiable or not. And why this works is because, first of all, B is necessarily a leader, because if B isn't a leader, then all other nodes must be a leader. Then for the second node, it can't be any of the item nodes, because if a single item node were sufficient, then it would imply that that item node by itself exceeds or at least meets the value V in the knapsack problem, which would make that knapsack instance trivial. So for any non-trivial knapsack instance, the leader set would have to be S and B. However, just this construction by itself doesn't work, because not all contracts are created. So any item that isn't in the knapsack solution doesn't have their contracts, the to and from to that node contracts created. Only the nodes in the knapsack solution will have their contracts created. And by definition, a proper leader set requires that those leaders create all of the contracts in the transaction graph. So how we can fix this is essentially after we want to construct the graph so that after B gets V ethers, give them enough Bitcoin to create all of the contracts. And so essentially we just create this artificial gate. And by introducing this node Y, such that when Y receives V ethers, which V again is the value that we want to reach in the knapsack instance, let's give the broker the sum of weights in Bitcoin, the sum of weights of all items. Then clearly that's sufficient to create all of the contracts and sufficient to create any remaining contracts. The problem with this is that it breaks or conflicts with our DMLS strategy that we described before. So previously why that worked is it would take S and B to be the leader set of size 2 necessarily. But now with the introduction of Y, we can take B and Y to be our leader set. And this would actually be sufficient for any flower graphs of this form. And in turn, B can dodge solving the knapsack problem, since they're receiving the sum of all weights, then they can just create all the contracts to all of the item nodes and not needing to solve the knapsack problem at all. So in order to keep using our DMLS strategy, we want to set up the flower graph such that the leader set, if the leader set is size 2, then it has to be B and S, given that our knapsack instance is satisfiable. So how we can do that is first we'll compute this value M, which is defined as the ceiling of the sum of all weights of all items divided by the minimum weighted item minus 1. And then we'll create M additional cryptocurrencies, which we call C1 through CM. Then we want to split our previous Y node, so back here, into many pairs, which we just call Y1, Z1, all the way up to Yn plus 1, Zn plus 1. And the idea is that each pair will give the broker a small amount of Bitcoin, whereas back here, Y gave our broker a lump sum, namely the sum of all weights in Bitcoin. So now we want to give it in small amounts and coins, cryptocurrencies, to unlock the next pair. So using our C1 through CM coins. So for example, Y1 Z1 pair would unlock the Y2 Z2 pair. And then overall, the graph would look something like this. So we're not going to explain it here, but it's described in the paper. But essentially, by this construction, what happens is B paired with any of the item nodes, or Y or Z nodes, independently cannot create all of the contracts, meaning that if F does indeed have a leader set of size 2, then it must be B and S. And as we described earlier, if B and S is the leader set, then B is essentially forced to solve the knapsack problem, just as we described before. And then we can then use our DMLS strategy with parameter 2 to test essentially whether B and S is a leader set that creates all of the contracts in the transaction graph. And then this completes our reduction from the knapsack problem to the minimum leader set problem. Thank you for listening.